Our goal for this video is to find the length of a parametric curve as t ranges over an interval from A to B. Just an example of where you might want to do this is possibly if the parametric equations are modeling the position of an object as it moves over time, and you want to find the total distance traveled by that object along a certain path. Might be a car or a subatomic particle, or who knows what it could be, but something that's moving depending on time along a given path. And we can do this. We can do this using calculus. So again, our goal is to find the length of a parametric curve where t is in the interval. And I don't know if you're familiar with this notation here, but this is all the t's included in the set of numbers from A to B. So as t ranges from A to B, in other words. Okay, so we want to find the length of this green line. In a practical sense, this would be like if this was a green piece of rope. If you could take the rope out and stretch it out straight and put it beside a ruler, how long would that green piece of rope be? All right, and as I said earlier, we can do this using calculus. So let's say we have a curve, capital C. That's like this curve here that we have. One slight stipulation is that the curve can't have any intersections. There's got to be a one-to-one correspondence between the t values and the points x, y. So if your curve went along like this and then somewhere crossed itself, then there wouldn't be a one-to-one correspondence, because one given point x, y might be associated with two different t values. One t value the first time it hits that point, and then another t value the second time it hits that point. So you can't have a situation like this. There needs to be a one-to-one correspondence between the points. In plain English, it means that we can't have any intersection points. And in order to find this arc length that we're looking for, not only do you have to have the equation written in parametric form, but the derivative of x and the derivative of y both have to exist. So if they're not differentiable functions, this method is not really applicable to find arc length either. But most of the time it is the case. So if you do have x prime and y prime, and the curve doesn't intersect itself, then here we go. The length of the curve over the interval from A to B is given by this formula here. And so this would be worth your time to take to memorize this guy. It's just a straightforward plug and chug formula. It's the integral from A to B, and so that's what t ranges over, where the integrand is the square root of dx dt squared plus dy dt squared. X and y are functions of t, and so you can take the derivative with respect to t. Don't forget to square each of those. Then you add those results together, then you take the square root of the result. Seems kind of like an arbitrary integrand. It's like where in the world does that come from? You'll actually see when you take Calculus 3, hopefully you'll take the following calculus course, you'll actually see where this integrand comes from. It actually comes from something called the gradient of some vector, which I'm not going to get into those details. But anyway, you'll see some of those details in a future course. But basically, if you're given the parametric equation, you do these things, you plug in these values, you integrate from A to B, out pops a numerical value because it's a definite integral, and that numerical value represents the length of the curve over that interval. Now, the last thing I'll mention in this video is the fact that this integral, unfortunately, a lot of times can't be done or can't be done easily by hand. And you can see why. You remember back in your early calculus days when you were learning integration, whenever you had an integral with a radical and something underneath, typically what you had to use was u substitution, where you chose the u to be the inside of the radical. But the problem is if that's the u and then you have a du, do you see how there's nothing else out here on the outside that could be your du? If you have t's or t squareds or whatever in your du, you can't fix that. And so that means u substitution often fails for these guys, unfortunately. So if you need an answer, Many of these require that you use a calculator, and if you can do them by hand, they almost have to be specifically constructed so that you can do them by hand, but most of these cannot be done by hand. There's no shame in that. So just pop out your TI, compute the definite integral, get the numerical answer, and that answer will represent the arc length of the curve. Now we're not going to do any examples in this video. If you want to see some examples of me working out some arc length problems, you can go ahead and fast forward to the next video.